Good afternoon, everyone. A warm welcome to this live session on new course on principles of digital communication. I am joined here by with my TA Rishu Raj. So we would like to sort out your queries if you have any, and we would like that you keep on posting them. So the first question that I have is why we are using different orthogonal functions to express a signal. What we have seen in modulation is that if you have a signal st, this signal st can be thought as composed of k orthonormal functions. So phi kt represents that these are orthonormal functions and ak are the coefficients of these orthonormal functions. So the question is, why do we use a bunch of orthonormal functions to express a signal st? Now I can also generalize this to this function So in lecture 5, we have also seen that a signal st can in general be thought like this, and this is what we know as double sum orthonormal expansion, right? What's the physical meaning? Before answering the question why we do this and what is the use of this, let us try to understand what is the physical meaning of these orthonormal functions. So the first thing is, let us take a discrete time signal because it's easier to understand this in context of discrete time signals. And let us have a discrete time signal xn, which I have said several times can be thought as an array, and in this array there are various numerical values filled in. In this example, I am assuming the numerical values to be real numbers. Now, when we are thinking about this discrete time signal, let us assume that I have another signal yn, which is an array like this. And let us now assume that I have multiplied these two signals. And essentially, when I multiply this element wise, I will have in the resultant signal only the value corresponding to this element present. Okay, let me number this as first element. Now you can see that from these bunch of real numbers that I had, by multiplying this signal by this signal yn, I can extract the numerical value of xn along this element. And this is one orthonormal or orthogonal dimension of the signal. Secondly, this is the second orthonormal or orthogonal dimension. This is the third, this is the fourth, and this is the fifth. So this discrete time signal, as you can see, has 5 orthonormal dimensions. Okay. In case of a continuous time signal, if I have a continuous time signal, which is like this, and I sample this signal, and if my sampling theorem is satisfied, again I will have collected the numerical values corresponding to the signal at time instances, let's say t, 2t, 3t, 4t, and so on and so forth. And then I can convert or store these numerical values again in an array. So I can go from this xst to xn. So again, I can think about this a signal xt as it is built using many orthonormal or orthogonal dimensions. And in this case, you can see that there are infinite orthonormal dimensions. So inherently what we can say is every signal has the numerical values, and you can separate out these numerical values by multiplying this signal with, in this case for example, with an impulse where you want to select the numerical value. Now when I do this, again coming back, that when I have a signal which I express like this, there are two things that are running in here. One is that this is the most generic modulation scheme. All modulation schemes can be derived from this generic modulation scheme. So for example, if I want to think of a PAM modulation scheme from this modulation scheme, I know that I just have one orthonormal dimension. If I want to think about COM from this orthonormal, from this modulation scheme, then I know that I will have two orthonormal functions. Okay. And if I want to have, let's say, larger than two orthonormal functions, then I am talking about orthogonal modulation schemes. And we have seen, I think, in the lecture on orthogonal modulation schemes, that we like these orthogonal modulation schemes because they are most power efficient modulation schemes. So we have seen the power efficiency of coherent orthogonal modulation schemes is 2 log to m. So as you have more signals, which could be had by having more orthogonal dimensions, you can improve the power efficiency of the modulation scheme. When I have a good power efficiency, this also translates to low probability of errors. So increasing power efficiency reduces my probability of error. So in short, we like to think about this generic framework because from this generic framework all modulation schemes can be derived. The one that we have covered in the course are derived from this generic modulation schemes, and the modulation schemes that we have not covered in the course can also be derived using this generic framework. And if you choose the number of orthonormal functions more than 2, then we go into the regime of orthogonal modulation schemes. And once you have these orthogonal modulation schemes, they are best for power efficiency point of view. And if you have a larger power efficiency, you in turn reduces the probability of error. If you can have infinite number of orthonormal functions, then we have also seen in one of the lecture that probability of error can be made arbitrarily small for low values of ethno. Ethno can be made as small as minus 1.59 dB. So hopefully this has answered the question, and let us take uh, let us take the next question, which is maximum likelihood detector is an optimal detector in the sense of setting optimal decision threshold that gives minimum error probability. And the question is, why is that? So the question is, when can I have minimum error probability? So what is the probability that you have made a correct decision given that I have transmitted hypothesis I? What is this probability? If you want to look at this probability, this is given by integration of PDF of or likelihood given that hypothesis I is transmitted. So this is denoting the received random variable. So y is the received random variable and small y is the numerical value of this random variable y. And this is the likelihood function given that we have transmitted hypothesis I. Now you will make a correct decision if the received numerical value falls in the decision region corresponding to hypothesis I, which I indicate this with tau of I. So what I am saying is, this is the likelihood given that we have transmitted hypothesis I, and if you integrate this likelihood function over the decision region corresponding to hypothesis I, then this integration will give you probability of being correct given that you have transmitted hypothesis I. Now what is the overall probability of being correct? Overall probability of being correct is given by first the probability that you have transmitted hypothesis I multiplied by probability of being correct if you have a hypothesis I, which, as I have uh, looked in the last page, this was this. So this is the overall probability of being correct. So the decision rule that we are trying to derive is when we can have minimum error probability. Minimum error probability can be obtained when we will be having maximum probability of being correct. Okay. So what we want to do is we want to maximize this quantity, right? Now, by using Fibonacci theorem, I know that I can always change the or change the way I do my integration, and this is this. Okay. Now what I wanted to do is I wanted to maximize the probability of being correct. The probability of being correct can be maximized when I can maximize this quantity, right? And what is this quantity? This is nothing but it is the posterior probability. Okay. So the rule is, if I want to max probability of being correct, this probability of being correct is maximized when this quantity is maximized. So this is when you try to maximize this, or you try to choose an hypothesis I for which this quantity is maximum. Okay. And so this is map rule, right? That we have seen in one of the lectures. Now what is an ML rule? An ML rule is same as the map rule. ML rule is same as the map rule when my priors are equal. Okay. So when this the probabilities of all hypotheses is uniform, this does not remain a function of I, and thus trying to maximize a posterior probability is same as trying to maximize the likelihood, and hence ML rule is same as the map rule given the priors are equal. So what we have seen is trying to minimize error probability is same as trying to maximize a posterior probability is same as trying to maximize the likelihood. One more point. Why should I choose ML over map. We normally use this ML detection rule because of the reasons that these a priori probabilities are not known. And of course, you have to restore to ML rule over map rule because uh, if the source model or the priors with which the symbols are transmitted is not known, then it is the safest to assume that all symbols are transmitted with equal probability. That will reduce the probabilities in max-min sense. Okay. Any question? So the question that we have is related to offset QPSK. Now, in general, if we are talking about offset QPSK, then because we have seen in the lecture that the main idea behind, so let me first draw the constellation structure of QPSK. So now in the idea behind offset QPSK is you delay one of the channel by 1 bit duration. That enforces that your bit changes by 1 at an interval of ts by 2. So namely, you can only go from this signal to this signal, or you can go from this signal to this signal, but these diagonal transitions are not possible. Okay. Now, this offset QPSK can uh, let you have the phase transitions of 90 degree if you are using a, a pulse shape PT in general. But if you further restrict your pulse to be a half cosine pulse, if your PT is half cosine pulse, then in the offset QPSK, you can have constant amplitudes. Okay. So to have constant amplitude in offset QPSK, we need to work with a special kind of a pulse shape. The pulse shape has to be half cosine or half sine pulse shape, and then in offset QPSK, you can have constant amplitude. If you don't use this half cosine pulses in offset QPSK, you can also have the phase transitions of 90 degree. And once you use the half cosine pulses, then offset QPSK is nothing but it is a minimum shift key. So this is what we have said in the lecture. So again, I repeat, the phase transitions are 90 degree are possible for any pulse shape other than the half cosine pulse. Okay. Because this question on offset QPSK is asked, I will like also to talk about pi by 4 shifted QPSK. So in pi by 4 shifted QPSK, what we do is we have we have uh, in pi by 4 shifted QPSK, we are having a regular constellation, and together with that we have a constellation which is pi by 4 shifted. Okay, so what we do is, let's say in 1 t by 2 symbol time, we are making a transition from this constellation to this constellation. That means if I have chosen a symbol in t time as this symbol, then after t by 2, I have to choose a symbol or a signal from this pi by 4 shifted pi by 4 shifted constellation. And this will ensure that you only make a phase transitions of pi by 4 at every t by 2 interval. So this you can read uh, yourself more in detail. I just wanted to give you some ideas about that there are these kind of modulation schemes that also exist. The only question is that how to analyze circular constellation schemes. Now, in case of circular constellations, the derivation of probability of error is much more complicated than in the case of square grid constellations, and hence there is not a very easy way to assess these circular constellation schemes, and they are also not used in practical systems. So we cannot have standard square grid constellations when we know that the number of bits that you are encoding into a signal or a symbol are odd. If B is odd, then these square grid constellations or rectangular grid constellations are not optimal, and then we have to restore to what is known as cross constellation, or the constellations which are not square grid constellations. For example, when M is 8, that means B is 3, then uh, the rectangular constellation is not optimal, and we need to have a little bit more complicated constellation for this M where M is 8. One example of that constellation is this constellation. So what you have is, for example, let's put us 4 signals on this inner circle, and let us put 4 signals on the outer circle. And let us try to find out the probability of error for this 8 constellation. Now, if I use nearest neighbors approximation, then the probability of error is simply n d min times q of root of eta p epsilon by 2. So the only two unknowns that we have is number of nearest neighbors and this power efficiency. Once we have found them out, then we can evaluate this probability of error. So number of nearest neighbors in this case is simple. So if I concentrate on this signal, this can be neighbor with this can be neighbor with this can be neighbor with this, and this can be neighbor with this. So the number of nearest neighbors in this case is 4. And then what remains to be found out is this theta p. Okay. Now you have to do some mental exercise before we can think about this, finding out this eta p. As this radius of the outer circle increases, and let's say it increases uh, beyond the point where these two distances are equal. So let me label this distance. Let me call this as t1 and let me call this as t2. So for example, if I'm increasing this radius such that the distance d2 is much larger than d1, then I would not be minimizing my probability of error, but what I would be doing is investing extra energy per symbol. And hence the optimum value of power efficiency for this constellation is obtained when this d2 is same as d1. Okay, this is the condition for optimum power efficiency. So for optimum value of eta p, d1 should be same as d2. Okay, now if we understand that, then using geometry I can find out this d1 and d2. Let me call this as capital R and this radius as small r. And I know that this is at 45 degree. If I want to think about this D2, I have to first find out what is this distance. This will be r by root 2 minus r. This square plus r by root 2 square will give me D2 square. So I am using the Pythagoras theorem in this triangle. And let me assume that r is some x times small r. So the first equation that I have is r by root 2 minus r whole square plus r square by 2 is d2 square, and I can expand this as r square by 2 plus r square minus root 2 r times r plus r square by 2 is d2 square, and this is r square minus root 2 r r plus r square is d2 square. And I know that r is x times r. So plugging that in this, we get r square minus root 2 x r square plus x square r square is d2 square. So from this, I can get an equation that is x square. So I have taken this r square outside, then I will get x square minus root 2x plus 1 is d2 square. Okay, so this is one equation that we have in here. The second equation that I can have, considering the inner circle, and let me call this distance as d1. So I know that r sine pi by 4 is d1 by 2. From this I get r is d1 by root 2. And thus from this I get r square is d1 square by 2. So now I can plug this value of r square in this expression, and I get d1 square by 2 x square minus root 2x plus 1 equals to d2 square. Now I use the fact that for optimum power efficiency d2 should be same as d1, and thus I get x square minus root 2x plus 1 should be 2. So from this I get x should be 1 plus root 3 by root 2, which is approximately 1.93. And once I have got this value of x, finding out power efficiency is easy. So power efficiency is d1 square by EB. And what is bit energy? Bit energy in this case. So before finding out the bit energy, let me find out the symbol energy. Symbol energy in this case is r square plus r square x square by 2 if all the signals are equiprobable. From this I get the average signal energy is this, and from this average bit energy can be obtained as r square 1 plus x square 2 divided by 3, because per symbol there are 3 bits, thus I need to have this factor of 3 in here. So power efficiency that I can calculate is d1 square by EB, and EB is r square 1 plus x square times 6. Alright, and we have already obtained a relationship between d1 and r. So I have already said that r square is d1 square by 2, and thus I get power efficiency is 12 1 plus x square. And I have already obtained the value of x, which is 1.93. So power efficiency will turn out to be approximately 2.54. Now, even though we could have solved the power efficiency for this case, but in general, this is going to be much difficult. So probability of error finally is approximately 4 times q of 2.54 by 2 times f naught. So now we have two more questions which are related. The question is how to find out this average symbol energy if the symbols are not equiprobable. So let me consider a simple constellation where I have two signals. Let's say one at d by 2 and the another one at 3d by 2. If we want to find out the average signal energy or symbol energy, assuming that these symbols are equiprobable, we have done that. We have to find out the symbol energy corresponding to this symbol plus symbol energy corresponding to this symbol, and dividing this by total number of symbols that we have if the symbols are equiprobable. In general, I can write the average signal or symbol energy by multiplying this so I have to multiply the average signal energy with the probability of this signal to happen plus average signal energy multiplied by the probability of that signal to happen. So this is actually how we calculated the expectation of a random variable, isn't it? So instead of dividing by the total number of signals, or symbols, you have to multiply the signal energy of a signal and multiply this with the probability of that signal to happen, right? And you can see if the signals are equiprobable, then P1 and P2 is simply half, because there are two signals and they are equiprobable, and hence we get to our same old formula. Then the question is that if signals are not equiprobable, are not equiprobable, how can I think about the decision regions corresponding to the signals? Now let me revise what happens when the signals are equiprobable. If the two signals are equiprobable, then we have seen that the decision regions can be obtained by connecting a line between the two signals and drawing a perpendicular bisector. Okay? So in this case, we will have two decision regions, which are also known as Voronoi regions in this case, because they are obtained by drawing perpendicular bisectors between the signals. Now, this is because we have seen that inner product of VA is simply n naught by 4 ln eta. And if the signals are equiprobable, this eta is 1 and ln eta is 0, and hence the threshold is 0. So if you have to find out the inner product of received value with the transmitted signal, this inner product should be 0, and by solving this equation you can derive the set of points V, which will help you in deriving out the decision region for the signals. And we have seen this is the equation for a perpendicular bisector between the signals minus A and plus A. Now if we have to think about the case when eta is not 1, that means the signals may have different probabilities, then instead of thinking about the vectors, because this case is complicated, let me think this in terms of the numerical values, a single value of A and a single value of a single received numerical value V. And this is simply this. Okay, so you can find V as n naught by 4 ln eta by A. So this will give you the equation of the line which will form the decision regions of the two signals minus A and plus A. So let me draw that and try to understand this little bit more. So we have said V is n naught by 4 ln eta by A. Let me assume that this signal has more probability, the higher probability signal. So let me draw the perpendicular bisector as well. So this is the perpendicular bisector. If this signal is of a higher probability, then in that case, ln eta will be a negative quantity, and this V will shift to the left of this perpendicular bisector. What does this tell me is, if this signal is of higher probability, then you should decide for this signal much more than you decide for this. Okay. What more, if I have a very large value of n naught, that means if my noise levels are too much, then this line will shift more towards the left. That simply means that if I have a very noisy situation, then whatever may be the received value, I should always go for the signal with a higher probability. Okay, so in short, you have a line which is not a perpendicular bisector but shifted little bit towards the signal which is of a lower probability, and this line shifts more if the value of n naught is larger. That means in extreme noise conditions you should only decide based on the a priori probabilities of the signal rather than on the received numerical values. Then the next question that we have is, when should I have SNR and when should I plot my results with EBNO? Let us take an example of BPSK. In BPSK, the probability of error is Q of root of 2 EBNO. So this is in BPSK in additive. So this is in BPSK in AWGN channel, probability of error. Now, for QPSK also, because QPSK has the same power efficiency as BPSK, the probability of error expression for QPSK is also same as that of BPSK. Okay, but if I compare this in terms of SNR, the probability of error formula for BPSK in terms of SNR is this, whereas for QPSK we have this formula. That means if I look from the SNR point of view, so this is for BPSK and this is for QPSK. So if I look from SNR point of view, it seems that QPSK is a poorer modulation scheme as compared to BPSK, because it simply says that in QPSK you should need a signal power twice as large to have the same probability of error as you would get in BPSK. But this comparison is little bit at fault because we are not taking into account that per signal in QPSK or per signal waveform in QPSK, we are encoding 2 bits, right? And thus we should compare the digital modulation schemes based on the EBNO requirement and not on SNR requirement, because SNR does not capture the spectral efficiency of various modulation schemes. So if we have not been able to take all your questions, we will reply to them in the forum, and we will conclude this live session here. Thank you very much for your patience and attendance.